Hello, everyone, and welcome to today's live broadcast, Bioburden and Biofilm Control in the Pharmaceutical Industry, presented by Dr. Mark Pasmore. We are excited to bring you this educational web seminar presented by LabRoots. To learn more about LabRoots, please visit www.labroots.com. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window and type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice that you will be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located on the lower right. Finally, if you have trouble seeing or hearing the presentation, please click on the support button at the top right of the presentation window, or use the Q&A button to let us know that you're having a problem. Thank you. Now I'd like to introduce Dr. Mark Pasmore. Dr. Pasmore currently manages the Research Center in the Sterility Assurance Department at Baxter Healthcare. His research includes biofilm analyses, rapid microbial methods, alternative sterilization techniques, and new product development. He formerly has held the position of Assistant Research Professor at Montana State University, Department of Chemical Engineering. In his role at Montana State, he was the Medical Project Supervisor at the Center for Biofilm Engineering, where he studied biofilms in infection and medical systems, such as hemodialysis systems. Additionally, Dr. Pasmore worked as a senior engineer at Steris Corporation, where his research involved the evaluation and development of sterilization and decontamination technologies. He has multiple publications and presentations in the field of biofilm research, and he is involved in several professional and standards organizations related to bacterial control and sterilization, including the PDA Task Force on Bioburden Biofilm Management. Please join me in welcoming Dr. Pasmore. I will now turn the presentation over to him.
Thank you, Judy. I appreciate that introduction. So welcome, everyone. I appreciate this opportunity to talk to you about bioburden and biofilm control in the pharmaceutical industry. Without any further ado, we'll go ahead and get going. So before we jump into it, though, I wanted to show you a picture of a beautiful biofilm before we start talking about the ones that aren't so friendly. This is actually a hot spring at Yellowstone National Park, and the colors that you see in that hot spring, the oranges, the yellows, the greens, are due to biofilm bacteria growing in that environment. All right, so if nothing else, my goals for this presentation are to get you to think about biofilms early, and if you're working in the area of microbial control, for planning for the potential of biofilms and bioburden contamination. All right, a little bit of an outline over what we're going to be talking about. So I'm going to give you a little bit more background on bioburden and biofilms, talking a little bit about its implications to the pharmaceutical industry, and then we'll get into some of those control ideas. We'll talk about design for control, detection of microorganisms, remediation of microorganisms, the potential for reoccurrence, and therefore the need for prevention, and then we'll do a little summary. All right, so Judy was kind enough to mention my role in the PDA task force. We recently just published a technical report on bioburden and biofilm management, and right here you can see an outline of the sections in that. Really good resource. I really like it. And if you notice, it actually kind of mirrors my presentation today. A few sections on kind of background and introduction, then talking about design, detection, remediation, and those type of topics. A couple things I stole from that. So the first one that it states early on is, I'm just going to go ahead and read this. It is important to educate engineers, scientists, and managers about the science of bioburden and biofilms, given the broad and complex challenge of bioburden management. To summarize that, what it really means to me is this is a team effort. These are complicated challenges, and we can't do it alone. We really need to work as an organization, whatever organization you're in, to be able to effectively tackle that. So with this, you may be wondering what I mean by bioburden when I say that. Essentially, bioburden are viable microorganisms in the manufacturing setting. These can be associated with personnel, with the environment, with the equipment, with packaging, with materials. But most critical, these are things that could end up in our finished product. So we really want to make sure that we properly control them so that we have safe product. All right, so a little background on biofilms. So biofilms are made up of multiple microorganisms. They're communities. These microbial communities attach themselves to surfaces, and given time, they'll produce extracellular materials that helps glue themselves to the surface. Bacteria have been around for approximately 3.6 billion years, and the fossil record suggests that biofilms formed as early as 3 billion years ago. And I mention this because it really demonstrates that these organisms have been around adapting to their environments for an extremely long period of time. So as you can imagine, they've adapted to quite a wide variety of environments and can be found virtually everywhere. If you've been sitting in on some of the earlier biofilm talks, you may have seen figures similar to this. I'm just going to step through it real quickly to talk about really what happens in biofilm formation. It happens in a series of stages. Usually there's an early attachment event where free-floating microorganisms attach to the surface. They'll do some early colonization and growth. Given enough time, they'll actually continue to grow and oftentimes develop much more complicated three-dimensional structures. And eventually you'll see detachment events. Those are usually sloughing or seeding activities. Sloughing meaning large chunks breaking off and potentially floating away. And seeding is actually a mechanism whereby the organisms dissolve their own matrix and float or swim away individually. So these are multi-species communities. So as you probably are aware, microorganisms actually come in a wide array of shapes, sizes, and behaviors, and that they once again adapt to multiple environments. And in most of those environments, there are multi-species biofilms. It's very uncommon to find single-species biofilms. It does happen in some extreme cases, such as when we put them under very harsh conditions, as we try to do when we're trying to prevent them in the manufacturing environment. But single-species biofilms is the exception, not the rule. And these organisms will adapt over time. If we put pressures on them, they will select for the most tolerant organisms, and you will see those being the most prevalent over time. And so to summarize that, essentially the way I think of bioburden in the manufacturing environment as many ever-moving targets. So it's certainly a challenge as we try to prevent these. All right, so going a little bit more into the pharmaceutical industry, there's quite a wide array of pharmaceuticals that are made. You are probably familiar with a number of them. There's oral dose forms, things, topicals, other different medications, and sterile injectables are some of probably the most challenging of those when it comes to a microbial control standpoint. So these are manufactured in a number of different ways. They could be a non-sterile manufacturing, a terminally sterilized where we sterilize the product after it has been made, and aseptic processing where they're essentially initially sterilized and brought together, usually with a final filtration immediately prior to filling the solution. So the need for microbial and bioburden control around these vary significantly. You can imagine an oral dose form that's going to go into an environment that already has a lot of microorganisms associated with it, the mouth and the intestinal tract. A few non-pathogenic organisms introduced in that environment are certainly not going to be the danger or safety risk that injecting those into the bloodstream would be. So as such, the microbial and bioburden control that we have to do vary significantly. The most significant of that is the aseptic processing, where we need to produce sterile product without having the tool to do some type of terminal sterilization. So what sterile basically means is that it's free from viable microorganisms and that it has an acceptable limit of pyrogens, which we'll kind of touch on as we go through. And this is becoming an ever increasing challenge for the medical and pharmaceutical industries. So the young gentleman in the picture here, his name is Alex. Alex is a type 1 diabetic, and as such, he needs to take insulin multiple times a day. And with diabetes, as he continues to grow older, he is going to have some challenges around his immune system. And so he'll need to continue to take medication, and that medication has to be free of microorganisms so he can safely take it without having risks of receiving an infection. And once again, this is an increasing population with things like oncology and autoimmune diseases, other diseases that have left a increasing portion of our population susceptible to infection. All right, before we go into some of the control measures, I wanted to talk a little bit about some of the myths that are out there around bioburden and biofilm control. The first one of those being that if you have had some good numbers on your detection methods, you're doing your microbial monitoring, and you have not seen high bioburden counts for a while, you're in a good point. That's not always true. So basically, yes, if you've had a good count, that's certainly not a bad thing. However, when we think about it, especially in the case of biofilms, where you can have surface-associated microorganisms that only seed or shed occasionally, you might go an extended period of time without any issues, then have a seeding or sloughing event and have your number spike above the acceptance limits. So just because you have recently had some good numbers does not necessarily mean you're in a state of control. All right, the next one is that high flow rates can control biofilms. And that's also not necessarily true. At the bottom is a figure illustrating essentially flow in a pipe. So the arrows represent flow rates, the large arrows being high flow rates and the small arrows being low flow rates. And like most piping, what you see is the highest flow rates in the middle of the pipe, and as you approach the walls, those flow rates reduce significantly, such that actually within depending on the flow rate, tens to hundreds of microns from the surface, you actually get into what's considered a viscous sublayer or boundary layer, where the flow drops to near zero and there's virtually no shear on that surface. And you can imagine with microorganisms being 1 to 2 microns in size typically, that a 10 to potentially 100 micron area where they can grow without stress is certainly plenty of room for a biofilm to develop. All right, the next one is around dead legs and the lack of flow being the problem with those. Now, certainly flow is a good thing for minimizing potential growth in these areas, but in the last comment I made that flow can't prevent biofilms, therefore it also, on the flip side, won't be your problem. Lack of flow won't be your problem with these dead legs. It's really the problem is they don't typically get cleaned out. They don't see the same removal and treatment regimes that the rest of the manufacturing would. And lastly here is that you can't remediate a biofilm. Now that's not to say biofilms aren't extremely difficult to remediate. They can certainly pose a significant challenge. However, they in most cases can be remediated. What I tend to see is that a lot of times when they can't be remediated, it's because either the source of the biofilm or sources of the biofilm can't be identified, or there is potentially a design flaw in a particular piece of equipment. So those type of issues may make it very difficult to remediate a biofilm. You might have to change out equipment or continue an investigation to identify where the problem really is. All right, before we jump into the pharmaceutical industry, I wanted to talk about a couple other industries just for comparison. So the semiconductor industry actually uses a lot more water than the pharmaceutical industry. A particular company can use as much as 1 million gallons a day of water, and that water needs to be very free of microorganisms. Microorganisms represent particulate that can affect their silicon wafer production, and therefore they do a very thorough job of controlling it. In fact, their controls are usually about 10 times more rigorous than what you would see in the pharmaceutical industry, or another way to say that is their acceptance levels are about 1/10 of what you would see in the pharmaceutical industry. So a lot of water, and even with that high level of control, you will occasionally see some type of colonization in their systems. And of course, there's a lot of expense involved. The picture at the bottom there is actually a representation of a water system in the silicon wafer industry, and a lot of expense associated with doing or controlling water to that level. On the flip side is the food and beverage industry, where you can imagine there's a lot of nutrients present. The nutrients for us usually make great nutrient sources for microorganisms as well. So cleaning and disinfection become very critical. And of course, the food and beverage industry do this very well on a daily basis. So it is possible to clean these, and sometimes really challenging materials to clean. Examples such as peanut butter, which getting off of a surface is certainly got to be some work for that industry, is certainly doable. And one of the ways that we'll talk a little bit more about is not only having good cleaning, disinfection, but also making sure their systems are as dry as possible. So worrying about things like drainability, not using water when they don't need to, things along those lines. So something to keep in mind as we're walking through the other slides. All right. Now coming to the pharmaceutical industry, I like starting with interesting pictures. I really like this one. This one is actually from a reverse osmosis membrane. The larger structures that you see in it are actually the spacers between the membranes. So this is, of course, a microscopic view blown up. And what you can see is actually a biofilm growing kind of right out in space, clinging to multiple of these spacer fibers. So a lot of times we think about biofilms as being surface associated, but sometimes they can be very much three-dimensionally into your fluid path. Okay, so I'm going to be talking about some of the challenges, and there's really four that I'm going to be discussing. The first one is the prevalence of microorganisms in the environment and the potential challenges that creates. Despite being an engineer, I'm not going to be using any equations. The closest thing I have to one is right here. And it's basically if you have bacteria and water and you give it enough time, you're really going to have a biofilm form. Now, what that time is going to vary significantly with your system, which microorganisms are present, and the nutrients available. All right. So kind of going into that ubiquitous nature, microorganisms are everywhere. They can enter your system, so you won't need to worry about ingress. And once they're there, they can proliferate. And so when I think of microbial control, one of the parallels I like to draw is a comparison with fire safety. I think it's because pretty much all of us in school or in our professional careers have had some type of training on fire safety, which, if you remember back to that, there's really three elements they tell you to control. There's your fuel source, there's your oxygen, and there's your ignition source. And similarly, it's true with bioburden control. You've got your nutrients, your fuel source. You've got your water, which could parallel pretty fairly with the oxygen for fire, and your microorganisms, your ignition source. That if you can control any of those effectively, you have a good chance of controlling your bioburden. Those are all very challenging to control, so there's a lot of work that goes into that. So when we talk about ingress, it's things such as leaks, human contact, cross-contamination. When we talk about water, controlling it through means, of course, minimizing, but that's often not possible in a lot of systems where you need water to make your solutions. Then you need to worry about drainability, pooling of that water, how long that water sits around. And where possible, if you can create harsh environments during your manufacturing, then you can minimize the potential for proliferation. The food industry uses this regularly. They call it hurdle technology, putting as many obstacles in the way of the microorganisms as possible. All right, so a little bit more on the contamination sources. In the pharmaceutical industry, touch contamination is probably our biggest source. Humans have a significant amount of bacteria associated with them. The estimates are that there's 10 bacterial cells in or on the human body for every human cell. So there's certainly a potential for contamination there. And a lot of those organisms are already growing in a surface-associated or biofilm mode of growth, so it's not too hard for them to switch into that once they're in the manufacturing system as well. Other sources include raw materials, water that's being used, air, which we are certainly designed for, but sometimes I think gets overlooked on the day-to-day operations within manufacturing. and then leaks and cross-contamination. So uh, I actually don't mind so much the leaks that we can see because we can pick those up and we can fix those. What really concerns me is when we have leaks that we can't see. For example, heat exchangers have the potential for having holes between the clean and dirty side, and when that happens, you have the potential for microorganisms crossing over and contaminating your product. All right, getting a little bit more into design, control, and prevention. So when you're designing systems, really it is about safety and quality, which to me the best way to do that is starting with a risk assessment. Basically looking at your system, going through it in detail and understanding the microbial risks that are involved. Those risks can be used in your designing, and that should include facility design, equipment design, water systems, as well as your process design. So looking at the potential for ingress due to those sources we mentioned, personnel, raw materials, etc. Also your proliferation times. These are times such as when you're performing your manufacturing, how long are you going to let your solution or your other materials sit while you're waiting to fill or moving on to the next step? If these are not bacterial static or bactericidal, there's potential for proliferation, and so you have to worry about how much time they're going to sit there growing. In addition to that, once you're finished with whatever process it is, how long are the systems going to be allowed to sit there before they're cleaned and sanitized? And once you've cleaned and sanitized them, how long are they going to be allowed to hold until you start your next manufacturing operation? All of those times have the potential to allow for microbial growth and therefore potential for risk for your next operation. And there is persistence and persistence prevention. And what I mean by that is you can have microorganisms getting in, you can have them growing, but you can also have them surviving your treatment. So working on preventing any risks that you have around those surviving that cleaning and sanitization. So that then can all be built into a cleaning, disinfection, and sterilization program, and then that should be trended. And we'll talk more about trending in a little bit. All right, equipment design, one of the parts I actually really enjoy. It starts with materials of construction. Whatever you're making your equipment out of, is it cleanable? Is it compatible? What are your connections? Are they welded? Are they seals? Hopefully there's no threads. Um, Threads can create a significant problem for growth in these areas. Filtration is certainly a useful component. However, filtration only is effective at preventing issues upstream of the filter. Anything after the filter can't be controlled by that filter, so it's usually good to place it really close to your next unit operation. You need to think about your moving parts. Valves and pumps, things like that can break down over time and create areas for microbial proliferation and retention. Also, part washers and troughs. So in many systems, not all of the components can be cleaned in place. They need to be taken off of the system and cleaned out of place. So those pumps and washers or whatever, the different components that need to be cleaned can be taken to the trough and cleaned there. Because they're going to be cleaned in these systems, those systems need to be maintained in a very similar level to your manufacturing system. If they're not, there's a potential for microbial proliferation in your washers and trough. And then rather than cleaning your parts, you could be actually contaminating them in these systems. So we already talked a little bit about dead legs. Those are certainly important drops. Really, you want to get rid of all of those that you can. If you have to have drops, which sometimes you do because you have components that are going to be connected and disconnected, they need to see the same treatment regime as the rest of your system. You need to make sure also that your systems are sloped and drainable and have proper surface finishes. If you're interested in finding out more about this, the American Society of Mechanical Engineering has a great standard, the Bioprocessing Engineering Standard, which really goes into a lot of depth on all these different components, and I highly recommend it for anyone who's working in this area. All right, so moving on to the next one. This is going to be our first poll. So I would ask the moderator to please load the poll. And for those of you, hopefully you're able to see the poll. And what I'm going to ask is that you look at the diagram there. There's an asymmetric connector, and that asymmetric connector can be connected in a couple different configurations here, configuration A and configuration B. And I'm going to ask you to choose which of those configurations is better from a microbial control standpoint. So take a second, take a look, and let me know which one you think is better. All right, hopefully everyone is putting in their answers. And if we could, hopefully that's enough time for everyone. If we could go ahead and wrap up the poll. All right, the poll has closed. And we have 63% that say A and 36 that say B. So looks like the answer that's preferred is A. A is actually a pretty good design. If you're looking from left to right, or if you're looking at it with flow going from left to right, and you're trying to drain this configuration, you can see that you can actually drain it without holdup, whereas with B, if you're trying to drain that, you could see that there might be holdup, which might create a potential risk for microorganisms. I have to tell you, actually, this was a trick question. Both answers are equally correct or wrong, depending on what you're actually considering with this system. Because A, although it's really great for draining, if you're looking also from left to right with flow, you could have, in a scenario where you're trying to clean it, if you have air entrapped in that cleaning solution, you could actually have air bubbles coming out of solution and collecting at the top part of that wedge there in A, and potentially creating an area where you're not getting your cleaning solution exposed to that entire surface. So I know this is a trick question, but it is really to get you thinking about that there is sometimes more than one issue that's involved with this design. Now, if we were reversing the flow, if the flow was actually going from right to left, then B is actually a really good design for that type of flow scenario, because your drainability is good and also your cleanability is good. But we can't always go from a small diameter to a large diameter, so it really depends on your system. All right, so this is the second question. This one really, I'm just going to ask you to use the question and answer box. We're not going to actually do this as a poll. This is an image of a water processing system. It's actually not a pharmaceutical manufacturing system. However, it has some issues with it. Some that I'm even concerned about just from a water handling standpoint, but definitely ones that I'm worried about if this were used for manufacturing in the pharmaceutical environment. So take a minute, go ahead and use your question and answer tool, and let me know if you see any issues that are occurring there. All right, so hopefully we're getting some of those in. Oh, here we go. I think they're coming up. All right, so I see threaded pipe concerns with threads and ball valves, potential dead legs. So good. You're seeing most of what's in there. It's great to hear that some folks are able to pick those up. There's a number of things. You've already picked up on a lot of those potential or threaded connections, potential dead legs, ball valves. There's also what you might see in here. In addition to the threads, there's leaks. There's actually dripping taking place. So yes, there's a lot of things going on here that you really want to fix if you're concerned about your bioburden control. All right. So moving on then to inspection and maintenance. Inspection and maintenance are really critical as well. So some of that has to do with the fact that equipment just fails over time. That given enough time, virtually everything is going to fail. And so you need to keep an eye on what's happening with equipment over time. There's the potential for corrosion, pitting, cracking, leaking, other things that can potentially create areas where biofilms or other microorganisms can set up and survive through not only during manufacturing, but during the treatment subsequent to manufacturing. So during inspection, making sure that those items are noted and addressed is important. The other thing that I've seen done with manufacturing maintenance is also using it for microbial inspection. There was a great presenter from J&J who did some talking about using it in the microbial control strategy, that regularly these systems are opened up, and when they're opened up, it's an opportunity to see what's going on in there. Um, there is always the chance, and I fully expect this is happening unfortunately across many industries, where you have a repair person that is opening up a piece of equipment, let's say a pump, for maintenance, and they see a slime that's growing in there, but they don't really think twice about it because they're there to fix whatever problem it is. They fix the problem and they put that pump right back into use. Well, of course, they're putting that microbial contamination right back into the system. So this is an opportunity, as I see it, to basically use this for microbial control, either educating those maintenance folks about the potential risks if they see something going on, discoloration, growth in there, or potentially having one of your microbial control folks walk the lines with them when they're doing their periodic inspections or maintenance, when they're opening up the system, have somebody who knows about microbial control working with them, educating them and checking out the different components as they're being opened up. All right, so this is, I guess, is a little bit of a summary of what we've been talking about under these parts of the control. So, um, you start when you're talking about pharmaceuticals, you start with your target product profiles, and then you look at your material controls, looking at your contamination sources, your operators. You look at your proliferation times, um, your early colonization. You try to eradicate that before it becomes a problem, and really this should be all based on your risk assessment. Okay, so that moves us on to the next challenge around bioburden and biofilms, which is the difficulty of detecting. All right, so when you're thinking about detection of microorganisms in a manufacturing setting, the first thing you need to think about is where you're going to do your sampling. Hopefully this is based around your microbial control plan. You're going to be thinking about, okay, what kind of sample am I taking? Typically, we take a liquid sample. There are occasions where we might take a surface sample, usually a swab. Did we pick the right location? If we are taking a surface sample, how accessible is the location we'd like to get to? We might be swabbing the tank, but the real issue might be in a valve upstream. Because biofilms are very heterogeneous. They don't necessarily occur consistently across your system. Once we have that sample, then we've got to take it to some type of analysis. Typically, that's an agar plate. Although there are some manufacturers, some vendors out there that are coming up with very interesting new ways to detect microorganisms. Um, but sticking with our old standby, the agar plate, how culturable are those microorganisms on the selection of agar? So there's always a question there about, are we being able to detect them due to the choices that we make there? And even if they do grow, what does a colony forming unit mean? If you have nice broken up individual cells, you should hopefully get one colony for every microorganisms you started with. However, if you've got biofilm detachment, you might have a chunk of 10,000 microorganisms that only grow up into one colony. So there's question about how effectively you can enumerate in some of those scenarios. All right, microbial detection for me is really more than just detection. It's really about microbial monitoring. As I mentioned, it really needs to align with the risk assessment. What are the critical control points? Where are the highest risks? And are you monitoring in those areas? What are your plans for, what's your sampling per batch? If you have an intervention, what's your plan for sampling around that intervention or maintenance and inspection? After you put the system back together, do you do some sampling to make sure that there was nothing introduced as far as contamination during that maintenance? And then trending. To me, this is one of the most important parts because, as I mentioned before, a single point only gives you a snapshot. It doesn't really tell you if you're in control. So understanding those counts over time and IDing, making sure you understand what type of microorganisms are involved over time. All right, so that moves us to the next of our challenges, which is decontamination. And so if you have ideal design, control, and prevention, hopefully you never get to a point where you need to remediate. your system, because if you have to remediate, especially if you have to remediate a biofilm, it's very challenging. In some cases, depending on what you're using to sanitize a biofilm, you might have to use 2,000, as much as 2,000 times the concentration of what a preventive treatment is. So it's kind of funny. I jumped straight to remediation and kind of skipped over that prevention piece at first. But the reason I did that is because really you want to be on the preventive side. You want to be proactive, not reactive when it comes to microbial control. Because if you have to be reactive, you're behind the eight ball. You really are going to be challenged to get that removed and dealt with. So ways to prevent that. We already talked a little bit about making sure that you have microbial barriers, minimizing your ingress of microorganisms into the system. You also want to, as we talked about, minimize proliferation of microorganisms in the system. You want to come up with good preventative cleaning and sanitization program. And then I've got anti-fouling on here. Now, when I say anti-fouling, I'm not really thrilled with some of the anti-fouling materials that are out there in the manufacturing environment, or that are being sold into the manufacturing environment. But what I'm talking about here is just making sure that you have the proper surface finishes, things along those lines to minimize the potential for bacterial attachment and growth. So those could include not only your surface finish, but things like, are your welds polished? You don't want to create attachment points due to welds or other issues such as that. Of course, we can't always prevent bioburden and biofilms from growing in the system. Occasionally we do have an issue and we need to be able to remediate that. And the very best way to remediate biofilm especially is replacement of your parts. So that's not a very popular one, especially if you have potentially millions of dollars invested in your manufacturing environment. You don't want to scrap millions of dollars of equipment to do your prevention. However, it's extremely effective. But where I'm talking realistically about here is, what about your disposables? You're probably not going to throw away a $100,000 tank or a $200,000 piece of equipment. But what about your replaceable gaskets, your rubber gaskets? Those are notorious places for microbial growth. You should be looking at those. You know, a $5 gasket to save you thousands of dollars potentially in lost product is certainly worth discarding that and starting out with starting over with a fresh one. So looking at those, gaskets, your seals, your other wearable components that you might want to replace. One of the next best ways to treat is mechanical removal. So if you can scrub away those biofilms, that's certainly a great way to remove them. Not always feasible within your manufacturing system. So what most folks rely on, what most companies look to, is bactericidal treatments, where you're going to chemically kill the biofilm. And then lastly on here, I've got cleaning, which is probably not quite as effective as chemical treatment, but certainly beneficial. And although I've got it last on the order because it's maybe not as effective as the bactericidal, most of these you're not going to use solely just in and of themselves. So usually you're going to use cleaning in combination with some type of bactericidal treatment to really give you a much more rigorous cleaning. And if you're able to, mechanical in combination with those, you might use all three of those last three with replacing of your disposable parts to really get yourself to a place where you're in control again. All right. Excuse me. When it comes to cleaning and sanitization, it is not a one-size-fits-all. I talked a little bit about the silicone wafer industry and the food industry. You can imagine that you can't design one cleaning regime that would be effective for both of those scenarios. Similarly, it's true in the pharmaceutical environment. Depending on what pharmaceuticals are being made, you need to tailor the cleaning and sanitization to that system. Typically, it involves some type of rinsing, followed by some type of cleaning, followed by sanitization. Hot water and steam are used very commonly in the pharmaceutical industry. Sometimes chemical sanitizers can work. When it comes to chemicals, you need to think about your concentration, your contact time, your pH, your temperature, and is it compatible with your surfaces? And I've got the next one underlined here because to me this one is critical and occasionally overlooked. Whether you're sanitizing via heat or via chemical treatment, you need to make sure that your treatment is effective over the length of treatment. And when I say that, that would mean, for example, if your hot water is entering a system at 80 degrees C for sanitization, but over the process of your whole system, it's cooling down such that when it comes out, it's at room temperature, there's probably a significant portion of your system that's not receiving any treatment. So it needs to go through it needs to be at an effective temperature, or if it's chemistry, concentration, throughout that entire length and over the entire time frame. So if you've got a 30-minute treatment, it needs to be effective over that entire time frame. All right, and then I highly recommend that you have some type of remediation backup plan in place prior to having a problem, because if you are shut down because your system's contaminated, it's not a very fun spot to be, and you want to have that alternative treatment in your back pocket. You could potentially use the same treatment as what you do currently, but usually you have more tolerant organisms that have potentially survived it in the past. And what it's going to take to make that effective is going to be challenging. So you're probably better off having some type of alternative just in case. I personally prefer some of the oxidative sanitizers, but there are certainly a number of things out there that can be used. All right, we're to our third and last question for you. So this one is around, and I don't know if this poll is actually available. Good. Okay, here it is. So the question is how do you know that your sanitization regime is effective in manufacturing? So there's some options here. You can be looking at your periodic trending. You could be looking at your design of doing the design of experiments, potentially validating it, and then of course there's the always tried and true cross your fingers and hope. So if you could take a look at those and give me some answers. Give everyone just a little bit of time here to pick their answer there. All right, hopefully everyone's finishing up. And we can probably go ahead and give them just maybe 10 more seconds and we'll close the poll. Okay. All right, great. Poll is closed. And it looks like the biggest choice with 44% is validated, followed by periodic trending of the flora, and then the design of experiments. And so what we currently do, the traditional way to do it, is we validate it. Now, that means we basically try the chemistry in there in a study in the system and we see how it works. Let me ask you, in the manufacturing environment, and this is not a poll, this is just for you to think about, does that tell you the effectiveness for treating bioburden? And I'm sorry to say, in some cases it doesn't, because in the manufacturing environment, one of the things we can't do is we can't introduce a challenge. We can't put microorganisms into that environment. Nobody wants us to introduce bacteria into something that we're about to make their pharmaceuticals in. So it's not sometimes a very rigorous challenge, the validation process. But it is the way that we currently do it. And if it's a problem for bioburden in general, what do you think it tells us about the effectiveness of biofilm treatment? Well, we're not even looking at the surfaces. Typically, we're just looking at what's happening in solution. So you can imagine there's some holes there. So those of you who put validation had the correct answer as it is today. That said, those of you who put microbial monitoring and kind of periodic review, that's my preference for really being able over long term to truly tell if you're in a state of control. It's really that long-term trending that gives you a better idea, I think, as to whether you're overall control. So both of those answers are correct answers. Obviously, the validation is what's currently being done. Hopefully, the companies that are doing this are doing really good jobs with their trending so that they can stay on top of that control. And then design of experiments. One way to actually get a little bit better idea of how effectively your chemistries or your heat or things like that are is you could do a benchtop study. You're going to have to do some type of minimal studies to make sure things are effective. I personally like having some type of benchtop studies. There are some ASTM standards out there for testing some of these treatments. If you're interested, those are listed here. Excuse me. One example that we've done at Baxter is actually growing up a biofilm. This work was done in cooperation with the Center for Biofilm Engineering. where we took stainless steel surfaces, grew biofilms on them, treated them with chlorine, and looked at what happened. And what you can see, the picture on the left, the green image is the untreated, and the picture on the right with more red in it is the treated. After the preparations, they were treated with live dead stain, which essentially treats live organisms or stains them as green, dead organisms as red. You can see there's a significant log reduction. And to me, just as importantly, is you can see a significant removal as well, which actually brings us into the next theme, which is the potential for biofilms being a reoccurring problem. So biofilms, if not effectively killed, can actually regrow quite rapidly. So if you only have a partially effective kill, you've essentially left a lot of microorganisms already sitting in your system waiting for the next favorable environment to grow back. And even if you do kill them, but you don't remove them, there's some risk. There was a study done that was by the Naval Labs that looked at the time for biofilm, at least in one particular environment, to reform after it had been killed. So they took a surface, a clean surface, they grew a biofilm on it, they timed how long it took for that to grow, they inactivated the microorganisms involved but didn't remove them, put some more microorganisms in and looked at the time for the biofilm to reestablish. And in their study, they showed a roughly 1/10 the time to reestablish the biofilm as it took to originally grow it. So certainly removal is a significant risk. And not only is it a risk for regrowth, of course, typically these are microorganisms that are sitting around and they have the potential, even dead, to put some different endotoxins and other pyrogenic compounds into your product. So it's also a risk from the patient standpoint as far as pyrogens. All right, so going on to biofilm remediation. Basically, my suggestion, as I've talked before, is be prepared. Really have a backup plan in place. Do a good investigation. Walk through your systems, open it up if you need to, take a look inside, look at your high risk areas. When possible, replace disposable components. Definitely replace anything that's malfunctioning or has issues. Then after that, you're probably going to need to come in with a multi-iteration cleaning sanitization process where you're going to cycle cleaner, sanitizer a few times. And then you're going to need to make sure when you do it, you're going to be at elevated concentrations and elevated contact times. That's really what it usually takes to be effective. So that's kind of the treatment measures. After you've done that, I would highly recommend that you do some elevated sampling for a while to really make sure you've returned to a state of control. And I kind of like this biofilm picture. This was done by our microscope group here at Baxter, and it looks like something's crawling out of this biofilm. So kind of like it from the remediation standpoint. All right, so moving on to the summary around what we've been talking about. Water is one of the main problems. Many of the microorganisms that are of issue are going to be growing in water. That we have challenges detecting these, so making sure you have a good strategy for microbial detection. There's always the potential that they can reoccur, so really making sure you have a proactive strategy. So continuing down that summary, really for the pharmaceutical industry, it's thinking about what your products are, designing effectively for those. So that's equipment design, your control strategies, so your processes, hopefully all based around a risk assessment. Then I highly recommend good maintenance programs and using that maintenance program to do microbial inspections as well. Really looking at your long-term monitoring and trending for your bioburden. And then if you do detect an issue, being ready to rapidly treat that. All right, so with that, I've given you a few references throughout the talk. Here's those summarized again. I believe there's going to be a PDF available, so these are some things that I highly recommend that you have on hand if you're looking to do some bioburden control. The first two especially, the later ones if you want to do testing around it. And with that, I'd like to thank some of the individuals and organizations that provided some of the images you saw today in the presentation. Also, this image, you may notice the name on the back of the jersey of number 11 there. It was the same name as on the title slide. So this gentleman is actually that well-dressed, red-headed young gentleman, Alex, that we saw from one of the previous slides. Alex is doing well with his diabetes. That the fact that there are good microbial control programs in place for the medicines he uses is obviously very important, and I wanted to take this opportunity to thank all of you that work in the microbial control area for the safety that you provide to your customers and patients. And with that, I'd like to thank everyone for your attendance, and I will be opening it up to questions.
Thank you, Dr. Pasmore, for that informative presentation. So it's time for Q&A. If you have a question you'd like to ask Dr. Pasmore, please do so now. Just click on the green Q&A button at the lower left of the presentation window, type your question in the box that appears on your screen, and click on the send button. We'll answer as many of your questions as we have time for. So let's get started. Our first question is, lately I have seen the use of heat to disinfect water systems, also steam. How effective is heat alone to prevent or remediate biofilm?
Very interesting question, and I'm going to hit it. Sorry, I don't know if you heard that first part of that. The interesting question, I'm going to hit it at a very high level. There's a colleague of mine who is currently putting together a publication on that, and I don't want to steal her thunder. But what I will say is that it can be very effective if you provide the proper temperature and time. So 80 degrees C certainly has the potential to inactivate at least the biofilms that we've looked at if you give it the appropriate time, and that you make sure that all of the areas that have the potential for biofilm growth are exposed. And when I say all of the areas, you can imagine if you have biofilms growing down into connection points like gaskets alongside of those, are you really achieving the full temperature throughout the entire component? Is that entire biofilm seeing that temperature?
If there are no more questions, I would like to once again thank Dr. Pasmore for his presentation. Oh, wait, I spoke too soon. Okay. When chlorine-based disinfectants are used, will stainless steel pipes get eroded over time?
It's another topic that I've certainly heard a lot about. Very interesting, and it's one of the ones where I wish I had an easy answer. So let me hit some of the topics around that. Chlorine can potentially damage stainless steel. That certainly can be an issue. There's a lot of properties around that really impact how damaging it is to stainless steel. So the chlorine concentration, it certainly has impact, as well as the pH. Acidic pHs can be much more destructive to the stainless steel than sometimes even the chlorine itself. But certainly chlorine at low pH, high acid concentration can be challenging. And then temperature. Hot chlorinated compounds can be much more damaging to the stainless steel than what they would be at room temperature. So there's a lot of different things that factor into how damaging that chlorine can be to the stainless steel. I think that maybe hits at a high level. There was the last thing around that is how well you do your rinses. I have seen really good control and minimal impact to stainless steel or metals in general over time if that chlorine can be effectively rinsed out between treatments. That typically your chlorine treatments aren't very long, but really can be damaging is if that chlorine is allowed to sit on your surfaces overnight or over multiple days. That's where I've seen the largest amount of damage.
Okay, so next we had a biofilm contamination in our purified water system. We were told to sanitize monthly using household bleach to prevent future contamination. Is bleach effective to get rid of and prevent biofilm contamination?
Okay, this is another one that's not a simple answer. I've seen some very good work where bleach has been used on biofilms, and uh, if you ever look at the Center for Biofilm Engineering's website, they actually have a video of bleach remediation of a biofilm, and they do show significant inactivation and removal over time. Now, this was about 50 ppm of free chlorine, and it was done over an hour. Even after an hour, though, they didn't completely remove or completely inactivate the biofilm. You see a very significant reduction, very significant removal, uh, but that is really going to be dependent on um, your concentration and your contact time. So once again, it can be used depending on how challenging your biofilm is. That may not be enough in and of itself. Um, Especially, you really do want to use it though in combination with cleaning as well, because bleach is going to be reactive, and if there are other organics sitting around, you might also not get it effectively to that surface. So multi-components to that question. My recommendations: make sure it's really clean so that you minimize the other contaminants that are around. Try to get it to uh, concentrations the higher. Uh, if you're doing biofilm, anything under 500 ppm would make me concerned, and you want to give it some extended contact time depending on what you can allow for. I, we've done some cases where even at that concentration, so we'll hit it for an hour or hours if we're concerned with an actual biofilm being present.
Do you recommend cleaning regimens as well as disinfecting? What is used?
So I'm sorry, Judy, I think you got cut off in the middle of that, and I'm not sure which one you were asking about.
Okay, let's just give that a minute. All right, you're asked, do you recommend cleaning regimens as well as disinfecting? What is used?
So yes, I would certainly recommend cleaning regimens as well as disinfecting. It's going to vary from organization to organization. We typically at Baxter use uh, various cleaning regimens depending on which pharmaceuticals we're making, and then we always follow it up with the sanitization. Um, those do vary once again depending on um, what chemistries are involved that you're trying to remediate, and then what your microbial load is. There is the potential. There are certainly some chemistries out there that will both clean and sanitize. Depending on what you're dealing with, you may be able to use one solution or one chemistry to do it all. At Baxter, we typically like a cleaner followed, I think, as I mentioned, with heat. So using the chemistry to do the removal and the heat to do any inactivation of anything that might be remaining.
Would you recommend other disinfectants besides CIP 100 and 200 for the CIP systems?
You know, this is an interesting question. Um, there are a number of chemistries out there, some very interesting ones. I'm not at a position at this point to probably make some good recommendations on that. We're actually looking at a few of the other alternatives currently in Baxter, and I don't have any data that I can report out on that. If things go well, we'll hope to be able to publish on that. So maybe next year we'll be able to talk more freely about that. At the moment, there isn't really any good recommendations that I can make of additional chemistries. I apologize for that.
A couple more here. Could you please give a list of proven disinfectants for cleaning the water systems?
Okay, so I heard part of that. The question is, could you please give a list of proven disinfectants for cleaning the water systems? I think this comes down fairly similar probably to the last question. Let me hit some of the high levels of that. Um, Basically, I personally prefer the oxidative disinfectants. So those include things like chlorine, ozone, hydrogen peroxide, peracetic acid. A lot of those chemistries give um, biocidal activity as well as removal, which makes them fairly effective against a lot of the biofilms and other issues. There are some detergents that certainly can help with both cleaning and removal. Depending on what your chemistry is, you may need to remove that as well. Sodium hydroxide works for a lot of the proteins and the lipids. So I will step back and say that it depends a little on your system. Since you're talking water systems, there are a lot of literature and information out there on, of course, ozone and hydrogen peroxide, peracetic acid, either by themselves, well, hydrogen peroxide by itself or in combination with peracetic acid are all potentials. You need to take a little bit of look at what your materials are in your water system. Are they compatible with those chemistries? And once again, heat's another way to inactivate. It doesn't do as good a job cleaning those, so you may have to combine that with a cleaner depending on your system. And I'm sorry, I know I'm being a little bit general, but as I mentioned earlier, some of these need to be tailored for the system you have. So it would take a little bit of a review of the water system to be able to actually completely understand.
Okay, we have time for one last question. What high temperature would you recommend?
So this is one that also has some variability in it. And I hate the depends answer, but it does, like so many of these things among microbial control, on what you're dealing with. And so let me start with, if you have any concerns with spores in your system, you need to be at steam temperatures. Typically, that's not an issue in most of the systems we're talking about, in which case you can use a hot water temperature. 80 degrees C is very common across the industry. It's nice in that it's certainly proven to be effective in a lot of different scenarios. You get some rinsing with it as well, and most of the regulators are pretty comfortable with that temperature. That said, depending on, once again, what you're manufacturing and what the final form of it is, the food industry does most of their pasteurization in the 55 to 65 degree range. So certainly for a number of microorganisms, you can go much cooler than 80 degrees C. So I know I'm giving you just a few bits and pieces there, but without knowing your system, I can't give you an exact number. I would certainly say nothing below 55. Typically in the pharmaceutical industry, I wouldn't even want to do 65. But there is some literature that suggests maybe we don't have to go to 80 degrees C for effective inactivation of these microorganisms. That said, depending on what your biggest concerns are, if they're regulatory risk concerns, you might want to go to 80 degrees C just because it's so widely accepted and so readily used. Hopefully that at least gets at some of the topics around that question.
Thank you once again, Dr. Pasmore. I would also like to thank our sponsor, LabRoots, for making today's educational webcast possible. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through February 2016. You will receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now. Thank you for joining us. We hope to see you again soon. Goodbye.